The last section of 6.5 deals with titrations. We will merge the concept of stoichiometry and acids and bases together. A titration is a technique where we can determine the unknown concentration of a solution by adding a known volume of a known concentration to a known volume of an unknown concentration solution. In this technique, you will use a special type of glassware called a burette to titrate the unknown concentration of solution. Typically, when I teach titrations, I show how we can get the unknown concentration of a solution using stoichiometric calculations. But we are at the end of the year and we are very limited with our time. So I'm going to show you instead how to use a very quick equation to come up with the answer. You'll notice that this equation looks very similar to the dilutions equation that we introduced a few presentations ago, the M1V1 equals M2V2. Remember that that equation is on your reference sheet. If we just modify that equation slightly so that we change the 1's to A's for acid and the 2's for B, which means base, you will get this equation. I'm going to go ahead and add an A on the left-hand side next to N and a B next to N on the right-hand side. A stands for acid, B stands for base. Hopefully by now we know that big M stands for molarity. So we're looking at the concentration of an acid, the volume of the acid given, and then this Na is going to be the number of hydrogen acids in the formula of the acid. On the other side, we'll see pretty much the same thing, but for a base. So we've got the molarity of the base, the volume of the base, and then once again we have the number of hydroxide ions in the formula of the base. If we take a look at the picture to the right, you will see a demonstration of a titration. You can see that the known concentration is at the top, and that is your titrant. It can be an acid or a base. In this case, it is a base. And in the flask, we have the unknown concentration. That is called the analyte. And in this case, it is the acid. The titration process generally begins by adding titrant to the burette. Remember that the titrant is of known concentration. It can be an acid or a base. And filling the flask with the analyte, which is the solution of unknown concentration. The next thing we want to do is we want to add an indicator to the analyte. The indicator here is going to be phenolphthalein. And you can see that it is clear, which means that this is actually going to be my acid, and that must mean that the base is in the burette. We're now ready to begin the titration, and slowly we will turn the stopcock of the burette and we will add base to the acid. You can see the start of a pink color upon the addition of the base to the acid. You are to continually swirl the analyte to even out the base and the acid with one another, and you will keep on doing this slowly, drop by drop, until you reach endpoint. Endpoint is when the color changes permanently. We want just a faint color change. We don't want a dark color change. You can see in figure 4, they've gone way too far. So you're going to add base drop by drop, each time swirling. As soon as that drop makes that pink color permanent and it doesn't go away, you stop. You don't want to go past endpoint. Now, endpoint is important because it signals to us that we've reached equivalence point. Equivalence point is when the moles of the acid in the flask are now equal to the moles of base that have been added. Now that the titration process is completed, we can take the volume of known concentration, in this case it was the base, and we can take those values, we know the concentration already, and plug it on the right side of the equation. And you knew the volume of the acid. So we can put that right here and we can solve for the missing piece. When equivalence point has been reached, there are no reactants left over. Both the acid and the base have neutralized each other, leaving behind the products of a salt and water. Remember that stoichiometric point or equivalence point means that the moles of the acid are now equal to the moles of the base. You don't want to forget to add the indicator to the analyte or you won't see a color change. The color change signals endpoint, and endpoint signals equivalence point, that point in which the acid and the base are now in equal amounts and they have neutralized each other, which is the stop of the titration. We always want to select an indicator that has a pH value close to that of the pH of the equivalence point of the titration. This picture just quickly shows you universal indicator, phenolphthalein, and phenol red, three of many of the different indicators out there. We used phenolphthalein in the example. Universal indicator would not be a good indicator to do a titration with because it has many different colors. You really want to focus in on an indicator that is one color as an acid, such as phenolphthalein. It is clear in an acid and pink in a base. Or like in phenol red, it's yellow as an acid and red as a base. Let's go ahead and take a look at a couple titration problems. The first question says, how many liters of 0.10 molar NaOH, remember that is your base, I know that because of the hydroxide ion, is needed to react with 0.125 liters of 0.25 molar HCl. That is your acid, and I know that because of the hydrogen ion. We really do not need a balanced chemical equation to do the shortcut, which is going to be NaMaVa is equal to NbMbVb. So we're just going to disregard this for right now. We would need it if we were looking at it in terms of stoichiometry. We know that the acid is HCl. There is one H, so we're going to put that for the Na. We know the molarity is 0.25 and the volume is 0.125 liters. We're going to then make that equal to the base. There's only one hydroxide in NaOH, so we're going to put a 1 again. And you'll notice that the concentration was given to 0.10, and there was no volume given. That's actually what you're solving for in this problem. So when we multiply the values on the left, we get 0.1245. We're going to leave it in our calculator. And on the other side, we get 0.10V. We want volume by itself, so we're going to divide both sides by 0.10. The volume turns out to be 1.2 liters. Now remember, I did not put the units of molarity and volume here. Volume was given to you originally in liters. That's why the final volume will also be in liters as well. So basically what this answer is telling us is that it would take 1.2 liters of sodium hydroxide to neutralize 0.125 liters of the 0.25 molar HCl. Alright, let's take a look at a second problem. Remember, because we're going to do this the shortcut way, we don't need the balanced chemical equation. We just need the equation MaVa, of course we got to put the Na at the front, is equal to NbMbVb. So the question says, what is the molarity of calcium hydroxide? That's our base. I know that because of the hydroxide ions. If 30 milliliters of the solution is neutralized by 20 milliliters of a 0.50 molar solution of HCl. So we know that's our acid. And once again, I know that because of the hydrogen ions. So now that I know my acid, I'm going to come over and I'm going to put 1 for N, because there's only one H in the formula. The molarity is 0.50, and the volume is 20 milliliters. And for the base, we have 2 hydroxide ions. I'm going to put that as Nb. I'm solving for the molarity of the base, and the volume is 30 milliliters. We're going to go ahead and multiply each side. So half of 20 is 10, and 2 times 30 is 60 MB. We want molarity, so we're going to divide both sides by 60, and that will give me the molarity of the base as 0.17. So your answer basically says that it's going to take 30 milliliters of a 0.17 molar calcium hydroxide solution to completely neutralize the acid in this problem. Alright, let's try one more problem. What volume of 2 molar solution of ammonium hydroxide is needed to neutralize 50 milliliters of a 0.50 molar solution of sulfuric acid? Remember that we don't need to use the balanced chemical equation because we're using the shortcut MAVA, NA is equal to NB, MB, VB. If we look at the problem, you can see that this is the base. We know that because there is a hydroxide ion there, and they're giving you the concentration, and we're solving for the volume. And then it's being neutralized with, and they've given you a volume and a concentration, and then you can see this is your acid, and we know that because of the hydrogen ion sitting in front. So now that we've identified the acid and the base, we're going to go ahead and just plug in some numbers. There are 2 hydrogen ions in H2SO4. The concentration is 0.50 molarity. The volume is 50 milliliters. And we're going to multiply that by NB. There's 1 hydroxide ion. We are solving for volume, and they give us molarity. There's 2 molarity, and the volume, we'll call it VB. So if we multiply 2 times 0.5 times 50, that's going to give me 50. And then we have 2 VB. We want to get volume by itself, so we're going to divide both sides by 2 molar, and that will give us 25 milliliters as the volume of the base. So it's going to take 25 milliliters of 2 molar ammonium hydroxide to neutralize 50 milliliters of 0.50 molar sulfuric acid. So this slide is going to talk a little bit about titration curves. Titration curves show the changes of pH during the titration process, and it is a great way to identify the pH of the equivalence point of that titration. You can see up in the upper left-hand corner, we have a titration curve that's going to start off as a strong base, and you know that because the pH is pretty high. It looks like it's about a 13 or a 14, and that strong base is being titrated with a strong acid. And I know that because if I go to the end point of the curve, you'll see that it's down here around 1. If I take a look at the graph to the right, you now can see that the pH is starting a little bit lower down. It's still in the base range. Remember, anything higher than a 7 is a base and lower than 7 is an acid. So we would say it's actually a weak base, and that's being titrated once again. We're down here around a pH of 1 with a strong acid. In the lower level diagrams, once again, we're starting off at a strong base, but this time we're being titrated by a weak acid. Now when we bring this back, you can see that we're at maybe a 5 or a 6. And this last one, the base is not very strong here. It's down here about 9, 10, and so we have a weak base that's being titrated with a weak acid. So there's lots of different scenarios of titrations, and being able to look at a titration curve and identify what your starting substance is, what's in the analyte is the starting point, and then what you're adding in the burette will be the end point. Drop the base. At this level, you only really need to identify the pH of the equivalence point of a strong acid being titrated with a strong base, or a strong base being titrated with a strong acid. What we're going to do here is we're going to look at the starting point, which in this case would be a strong acid. We're going to draw a line tangent to that starting point, and then we'll notice that at the top we're looking at being titrated with a strong base. We're going to draw another line tangent to that curved line. We're then going to find the vertical region, and we're going to bring that up and down until it intersects those two lines. It's at that point that we're going to find the halfway point of that vertical region. And when a strong acid is being titrated with a strong base, that halfway point will always give you a pH of 7. In this titration curve, we are actually starting with a strong base. I can see that because I'm up here about 13 or 14. And it's being titrated with a strong acid because it's down here about 1. So I'm doing the same thing I've done before. I'm drawing lines tangent to those starting and stopping points. I'm finding the vertical region, and I'm going to draw it up and down until it intersects those two lines. And then once again, I'm going to find the halfway point of that vertical region. And you'll notice it's also a pH of 7. So any scenario where a strong acid or base is being titrated with another strong acid or base will always give you a pH of 7 at equivalence point. This last curve is showing us a titration of a weak acid. Now I know this is weak acid because it's down here at a pH of 2, and it's being titrated by a strong base. And I know that because I'm up here at about a pH of 13. You're going to do the same thing you did before. These are a little flatter regions, but we're still going to draw the line tangent on each of those plateaus. We're going to find the vertical region, and we're going to extend it up until it intersects and down with the two lines. And we will once again find the halfway point. You'll notice this time that the halfway point will bring us back to a pH of 8, not 7. The only time the pH will be 7 at equivalence point is when a strong acid or base is being titrated by a strong acid or base. In this case, the weak acid is being titrated with a strong base. We know bases have a pH greater than 7, and so the equivalence point will have to be greater than 7. In this case, it is 8.